So it's a pleasure to have Shannon with us for our AMO seminar today. Shannon earned his PhD working on creating Bose-Einstein condensates on atom chips at the University of Swinburne with Peter Hannaford and Andrei Sidorov. And then he did a postdoc at the University of Amsterdam with Klaus van Rooten and Robert Sprio, working on similar topics with atom chips. And then he moved to a research scientist position with initially with Matthias Weidemuller, but then working independently at Heidelberg, where he set up experiments that were really the seminal work on energy transport mediated by dipole interactions in ultra-cold Rydberg gases. And in 2017, he moved to the University of Strasbourg and continues to work on the very interesting dynamics of Rydberg atoms in ultra-cold gases. And I believe he's going to talk to us today about some of his most recent results there. So please, Shannon, take it away.
Okay, thank you very much, Tom. I'll just share my screen. Good, so thank you again for the invitation. It's really a pleasure to be able to present some of our work here. Yeah, one day I hope to also visit in person, but for now, I guess this will do. So I hope you can see my screen just fine. Yes?
Yep.
So today what I want to present to you is some experiments we started actually quite a few years ago. To give you a bit of the backstory, basically what we were trying to do is understand in a little bit more quantitative way, maybe how strong interactions between atoms excited to Rydberg states in an ultra-cold atomic gas, how they behave dynamically. So in particular, if we can find some general principles governing the dynamics of these strongly interacting systems. And it's been a long and winding path, and I would say maybe 2 years ago now, actually, we had a bit of a breakthrough in our understanding. And since then, actually, we've been discovering more and more connections between the dynamics of this strongly interacting atomic system and complex system dynamics, which is found in very diverse areas of science. And so that's what I wanted to present to you today, actually, a little bit of our recent insights into these physics and connections, even beyond physics. So maybe just a very brief introduction, although I'm quite aware there's several experts in the audience. So our experiments focus on ultra-cold Rydberg gases. So these are basically just trapped atoms in an optical trap that we illuminate with a laser field, right, which excites the atoms from the electronic ground state to some high-lying Rydberg state with a principal quantum number around, I don't know, 60, 70 typically, right? And as you know, the typical size of an atom in the electronic ground state is maybe an angstrom or so. But when you go to these very high-lying Rydberg states, the spatial extent of the Rydberg wave function can become orders of magnitude larger, right? Scaling with the principal quantum number squared, right? And even approaching 1 micrometer or more. And so associated to this is that these Rydberg atoms, they acquire giant dipole moments, electric dipole moments, and therefore they can also interact very strongly over very large distances, at least with respect to our experiments. So we can have interactions of the order of tens of megahertz in frequency units, extending over distances far beyond, let's say, the typical interatomic spacing, so up to 5 or even 10 micrometers in some cases. And so for us, that's the interesting aspect, I guess, at the moment, that by exciting these atoms to the Rydberg states, we can induce very strong and controllable interactions between the atoms. And this makes this system extremely versatile for exploring many-body physics and in particular many-body dynamics. But I've been working in this area of Rydberg physics almost 10 years now. And I think one of the things I appreciate the most is that we are continuously discovering connections to other areas of science. And I've had the opportunity to work on just a little bit on numerous topics where Rydberg atoms are more or less the tool or the way to control the interactions in order to explore some other interesting physics. And this can range, for example, from extreme nonlinear optics using the Rydberg interactions as a nonlinear optical medium, Rydberg dressing, where you can create or engineer new phases of matter by tailoring the two-body interaction potential, open quantum systems, as was already introduced for the study of energy transport processes, for example, few body physics, molecular physics, ultra-cold plasmas, in RISE you have a lot of expertise, and even using these strongly interacting Rydberg states as atomic sensors. So that's, for me, I think one of the shining features of this Rydberg platform is the versatility of this system. You can use it to explore all types of different effects. So today I'm going to focus actually on what I think is a relatively new twist, and that is the application of Rydberg atoms now to study complex system dynamics, which is more typical, for example, in biology or even social sciences. So what is a complex system? This is something which is notoriously difficult to define very precisely, but the essence is that if you have a system of many interacting entities, particles, they can produce collective effects or emergent effects that cannot be readily predicted from their individual behavior, right? And so this is, of course, a very general concept. It applies to physical systems, for example, turbulent fluids, atmospheric physics, biological systems, for example, the signaling in neuronal networks in your brain, ecological or geological systems, and even social systems, for example, human behavior. This is a picture of a La Ola, a Mexican wave at a football stadium, which turns out to also exhibit extremely fascinating emergent properties associated, with the propagation speed of this wave and other features. So for me, this is kind of interesting because this umbrella of complex systems is something that can actually bridge many different fields, and it's of interest in mathematics, in physics, of course, chemistry, biology, philosophy, social science, you name it. Yeah. But of course, in atomic physics and condensed matter physics, we're very familiar with these concepts, right? And I would say complex systems science is not so much about how complex your system is, but more a way of thinking about the system, right? So instead of trying to understand from first principles the microscopic properties of the system, how this equates now into a phase of matter, it's more about looking at the system as a whole and treating it as a complex system. And sometimes maybe it's not possible to make this microscopic connection, right? For example, in the case of social systems, for example, but nonetheless, you can find principles or laws governing the behavior of these systems, which turn out to be extremely powerful. So on several occasions, I guess people have tried to define this in a more concrete way. I like this paper here, which is published in European Journal of Philosophy of Science, which, rather than trying to define complex systems, more or less did a survey of the field of many different results which are under this umbrella, and tried to identify some common characteristics which, let's say, are associated with what we call complex systems. And just to name a few of them, this includes, of course, some form of nonlinearity, which gives rise to these emergent properties, which are not trivial. Feedback is very important. Some characteristics which can be said to be emergent. Robustness, typically to initial conditions or microscopic properties, is very important. The spontaneous formation of order, and also hierarchical organization. And so what I want to do today, hopefully, is convince you that many, if not all of these characteristics are also present in the dynamics of a long-range interacting and driven ultra-cold Rydberg gas. I guess I should say I'm happy to take any questions. If you're game to interrupt me at any moment, please do, and I'm happy to answer anything. So maybe a few words on our experimental system. So the most recent experiments we've been doing is with an ultra-cold gas of potassium atoms, so laser-cooled atoms in an optical trap, which we focus very tightly in one dimension to form this sort of quasi two-dimensional geometry, right? And we typically have something like 10 to the 4 atoms in this trap at a temperature of 20 microkelvin or so. And while we like to think that we have these atoms well under control, in reality, that's probably not strictly true, since these atoms, I mean, 10 to the 4 atoms moving randomly in space with random velocities, and then also interacting with this laser field, which we use to excite these atoms to the Rydberg states. So when we excite the atoms, right, so we start in the electronic ground state of potassium, which is the 4s1/2 state. Then we shine in this laser. If this laser is tuned to resonance with a particular Rydberg state, right, then you can excite some of these atoms at random to the Rydberg state. But as a consequence of these very strong interactions, then in the vicinity of an already existing Rydberg atom, you get an additional energy shift, right? This is the Rydberg-Rydberg interaction energy, which can be large compared to the energy scale associated to this coupling. So for example, the line width of the laser or the Rabi frequency. So what that means is within a characteristic volume, it becomes extremely unlikely to excite a second excitation. And this you know, I think, is the so-called Rydberg blockade effect, whereby a single Rydberg excitation suppresses subsequent excitations. And this can give rise to very strong spatial and temporal correlations in the system, which have been studied in numerous experiments now for quite a few years. In the experiments I present today, we do something slightly different, and that is we tune our laser slightly off resonant, such that it becomes extremely unlikely to create a first excitation. But once you have this first excitation, it now becomes resonantly possible to excite a second atom at a characteristic distance, which is called the facilitation radius, right? And this is sometimes also called the anti-blockade effect. I prefer facilitation for describing, let's say, the collective dynamics now of the system, because once you excite, you know, a second Rydberg atom, then of course it becomes resonantly possible to excite tertiary and so on. So you have these sort of excitation clusters which can build up and grow and propagate through the system. So
Shannon,
one more
a question
word on the experiment. Yep.
So you said these were very two-dimensional, but I'm trying to get a feeling. So it's two-dimensional in the sense that it's much less than the other directions, but how does that third dimension compare to like this blockade radius or facilitation radius or interparticle spacing or these other length scales?
Yes, so the axial dimension is about 1 micrometer, I think, compared to the facilitation radius, which is around 3.5 micrometers. And the interparticle spacing is probably of the order of 1 micrometer as well. So in a sort of atomic gas sense, concerning the motion of the particles, I would say it's still kind of 3-dimensional, but with respect to the excitation dynamics, it's quite well described by a 2-dimensional system. Okay. So how do we probe this system now? Actually, we have 2 main ways in our experiment. One is we can shine a resonant laser, which is resonant to the ground to excited state transition of the potassium atom, so not using the Rydberg states, just some low-lying states. And then the atoms, of course, they absorb some of this light, and so then we can image that onto a camera. And we look from the side here, so you can see this sort of pancake-like shape, right, looking from the side, where the brightness of this signal tells us basically what the local density of ground state atoms are in the trap. So we have some measure of the ground state density, and not so much spatial resolution, but at least in 1 dimension, we can analyze the density distribution. Or we can apply a large electric field at a moment of time. And what this does is it ionizes all of the Rydberg atoms which are inside the gas, and then guides the ions to a microchannel plate detector where we detect the voltage spikes. And then we can integrate these voltage spikes in order to determine basically the total number of Rydberg excitations in the gas at a moment in time. So both of these detection techniques are destructive, but they give us different information. So in one case, we can access properties of the ground state distribution, and in the second, the number of Rydberg excitations. So today I'll show you 2 experiments, and then hopefully, if I have time, also a neat way maybe to interpret these experiments. So the first experiment concerns the early time growth dynamics. So starting with all the atoms in the ground state, we shine on this laser, and then we watch basically how the Rydberg excitation number grows. And we found a cute analogy to the dynamics of epidemics like we're all living through right now, which turns out to be rather deep. So I would like to maybe convince you of that. So first of all, a few more words on the microscopic processes. So this is a zoom now of our atomic gas where we have a Rydberg excitation present somewhere. Okay. Then there's a characteristic distance called the facilitation radius where it becomes possible to excite a second excitation. And this is our facilitated excitation process, whereby a single Rydberg excitation in the neighborhood of a ground state atom produces 2 Rydberg excitations. Okay, and this is going to provide the nonlinear ingredient of our complex system dynamics. And the rate of this we call kappa, this facilitated excitation rate. Of course, once you have a Rydberg excitation, it can also decay, for example, by emitting, spontaneously emitting a photon, right? So we have a decay rate, which takes us from the Rydberg state back to the ground state with a rate gamma. And because our laser is on all the time, it's just detuned from resonance. It's also possible, although rare, to off-resonantly excite an atom from the ground state to the Rydberg state. And we call that rate tau. You know? And so for the experts in the audience, you would be aware that this is already a very extremely simplified picture to reduce the physics to just these three rates. But it turns out that just considering these 3 processes with some effective coarse-grained scale for example, for this facilitation rate, does a wonderful job for describing this experiment. This is again the consequence of this complex systems approach, that the dynamics on larger scales is not very sensitive to the microscopic details. So if I take this already grossly simplified picture and go a little bit further, maybe you could imagine deriving a very simple classical rate model now for the Rydberg excitation dynamics, right? So this is a derivative of the number of Rydberg excitations in the system, grows according to this facilitated excitation, right? And this has a rate kappa times the density of ground state atoms in the region times the Rydberg number already pre-existing. It decays according to this spontaneous decay rate, and there's another growth term, which is this off-resonant excitation. And so what we think is a sort of an interesting regime is in the limit where this nonlinear growth term is larger than the decay, and in turn also larger than this off-resonant excitation rate, right? And so in that case, if you can neglect these last 2 terms, then from such a simple differential equation, you might actually expect that the number of Rydberg excitations in the system will grow exponentially. And then just to put some scales on here, so we use for these experiments the 66p1/2 state and a detuning of 30 megahertz. This is much larger than the line width of the laser and also the Rabi coupling. The facilitation radius is around 3.5 micrometers if we just estimate it from the Rydberg interaction potentials. The facilitation rate is something we can tune. It's proportional to the laser intensity, and we can vary this in the range from 0 to around 10 kilohertz per atom, because it depends now on the number of atoms that meet this facilitation condition. The spontaneous decay rate we calculate is a little less than a kilohertz, and the off-resonant excitation rate is well below 1 hertz per atom. So even integrating over the whole cloud of 10 to the 4 atoms, that gives us a cloud integrated off-resonant excitation rate of around 1 kilohertz. So the experiment we do is a so-called seeded growth experiment. So what we do is we shine the Rydberg excitation laser on resonance for just a very short moment, 4 microseconds. And this creates on average something like 8 Rydberg excitations at random positions in the gas, right? So a very small initial density of Rydbergs. And then we switch the detuning of our laser to 30 megahertz, and then we leave it on continuously with an amplitude that we can vary so we can control this facilitation rate. And so then this is sort of typical data. On the vertical axis, we have the number of Rydberg excitations in the system. And then on the x-axis is the time. So you see this is in milliseconds. To give you a sense of scale, the Rydberg lifetime is around 100 microseconds, right? So this is several Rydberg lifetimes, right? And what we see in general is very fast growth, right? So even within one lifetime, we get 4 or 5 doublings of the Rydberg excitation number, right? But it clearly deviates from an exponential growth law. That's this blue line. And the other interesting thing maybe is that we see this population saturate around 700 Rydberg excitations, which is well below what we estimate to be the system size limit. So if you calculate the volume of the cloud, compare this to the facilitation rate, even assuming a relatively low filling, this is well below what we would expect for the let's say maximum number of Rydberg excitations that we can have in the gas. So then maybe motivated by
can I ask a question?
Sure.
So in this plot, if you continue going, does it stay flat for much longer, or what, there is something else happening?
Yeah, I'll come to this in the second experiment. It's very interesting what happens there. Yeah, we deliberately left this to relatively short times, and I'll explain. I'll come back to this. Yeah. So motivated by CNN recently, we decided that maybe we could plot this data in another way. So instead of plotting the number of Rydberg excitations versus time, what we plot is the instantaneous excitation rate. We call this C prime, which is basically the rate at which we create new excitations in the system. It's basically the instantaneous number times the decay rate per Rydberg atom, right? And then we can plot this against the cumulative number of excitations that have been created in the system, which is basically a time integral of this, this instantaneous excitation rate from 0 to t. Yeah. And there's a very nice thing when you plot the data in this way. So this is this C prime versus C here. Then exponential growth should be a straight line, or is expected to be a straight line with a slope on a double log scale of 1, right? So it's a power law with an exponent of 1. Yeah. And what we see from the experimental data plotted this way is again a straight line. So it suggests something like a power law growth, but with an exponent which deviates strongly from the exponential growth law. And it turns out that this sort of sub-exponential growth is a hallmark of complex system dynamics, right? And the slope of this graph, which is the exponent of this excitation rate versus cumulative rate, is an emergent characteristic of the system, which can actually tell us something about the many-body system. And just to give you some intuition for this, what this p value corresponds to, if it's less than 1, it's called a so-called deceleration of growth, right? And it tells you that as the system evolves in time, let's say in the first generation, maybe I start with a single Rydberg excitation, and then I have 5 children excitations, right? In the second generation, then you have maybe 3. In the third generation, maybe you have only 1. And so eventually the growth slows down, right? And so this kind of hierarchical nature of the growth is can explain basically this sub-exponential behavior of the excitation number as a function of cumulative excitations. So this kind of graph and this sub-exponential growth is something you've seen before, because we were all recently forced to become experts in these kind of growth laws. I'm just trying to place this. Okay, can you see the title properly, or?
Yeah, we don't see that picture.
You don't see a picture now?
No, we don't see what you're moving around. It's not in the way for us.
Okay, great. So this is actually real data of the COVID-19 epidemic, right? For different countries now, monitoring the rate of new cases scaled per million versus the cumulative number of cases, again plotted on a double log scale. You know? And this is, of course, the early phases of the outbreak, right, where we were seeing rather rapid growth of the infections. And a remarkable thing is that all of these curves, independent of the geography, the nationality of the people, and so on, follows a rather universal scaling law, right, which is very similar to the one that we saw with our driven Rydberg gas, right? And this, in fact, has been known for a long time and has been studied for many different epidemics as the generalized growth model, right, which relates this incidence rate to the cumulative rate to some power p. This is a deceleration of growth parameter again. And R naught is an important parameter which describes the initial rate of growth. And the interesting thing is that for real epidemics, this p-value also varies, right, from values close to 1 corresponding to exponential growth. This would be common for diseases which can spread easily, for example, respiratory illnesses that spread through the air, right? Whereas diseases which require close contact, you know, like HIV, AIDS, for example, generally have p-values which are smaller than 1, right? And looking at data from China recently, also initially it was very close to exponential growth, but after containment, the p-values actually decreased. And so that shows it in an epidemic. In fact, you can even, to some extent, control this p-value depending on what kind of control strategies are being implemented. So this was interesting for us, and we wondered if there were similar mechanisms at play, or if we could learn, you know, something from these kind of interpretation of real epidemics, learn something about the microscopic physics governing the dynamics of this driven Rydberg gas. And actually, we think the analogy is quite deep, because even at a microscopic level, we can actually assign these processes that I introduced to the typical types of processes you have in an epidemic or in the spreading of a disease. So if we associate a Rydberg atom as a diseased atom, you know, the purple minion in this picture, right, and a ground state atom as a healthy minion, then this facilitated excitation process is equivalent to the transmission of an infection. So we have a infected atom, a healthy atom gives me 2 infected atoms. Right? And spontaneous decay is like a recovery process whereby an infected atom just naturally recovers, right? And it turns out these 2 processes compete, you know, and can be described by a model which is called the susceptible infected susceptible model, which is widely used not just for studying epidemics, but also for as a model for non-equilibrium phase transitions in general. So to illustrate this, if I do a simple simulation where I have a grid of minions, most of which are healthy, and then I put an infected minion here, and then this infection spreads to nearest neighbors, then what you see as a function of time is the infection is spreading, basically leaving behind a disk or a region of infected individuals. And if we wait long enough, then this infection will spread through the whole system and reach some kind of an endemic state. And so now, depending on this ratio of the facilitation rate to the decay rate, or transmission to recovery, we have a transition between an absorbing phase, where basically the whole system is healed, independent of what the initial conditions is, to what we call an active phase, where even starting from a single infected individual, eventually the infection will spread through the whole system, and you will have some macroscopic population of infections in the system. And this is a second order phase transition, so it has a critical point, which in this simple, let's say 2D spatial model falls in the directed percolation universality class. So it's a real second order phase transition like you're used to studying. It has critical properties associated to this, and it would be interesting then experimentally to study these properties and learn something about the universality class of this system. So one of the features in our experiment, of course, and it's harder to do in a real epidemic, is that we can easily tune the facilitation rate, right? So the data I showed you earlier was for the largest values of kappa, right, which gave this power law growth with an exponent of 0.6. And what you see now as you decrease this facilitation rate, we see 2 things. One is that the stationary density is reducing. And the other is that the slope here, or the deceleration of growth parameter, is actually decreasing, right? And actually, we can also identify something like a phase transition. Here, for above a critical value of kappa, we have an endemic population, so we have a stationary density above 0. Whereas for some of these curves, it looks as if there's some slow relaxation back to a state where basically the system would be inactive. And we can call this maybe a subcritical phase. And so the interesting thing is that in the incidence rate or the Rydberg number, we see something like a transition from this inactive phase to an active phase, right, at a well-defined value of kappa. But unlike an ordinary phase transition, we don't see universal, or it doesn't appear to be universal critical exponents. So we see in this active phase actually that this growth parameter, or this deceleration of growth parameter, looks like it's asymptoting to a value around 0.6, right? Whereas in what we call the subcritical phase here, it looks like it's continuously varying and reaches much smaller values. And in all cases, the deceleration of growth parameter is less than what we would expect from sort of a mean field type ansatz, where we assume that the infection can sort of spread isotropically in space. So this is interesting, and it's an interesting open question, I think. What's governing now the critical properties of this transition?
Is this process robust enough to initial conditions? Say like the time that you use the resonant laser, like instead of having like 8 initial seeds, you have like 16 or 30 or.
And the general behavior seems to be quite robust. In fact, we have very large fluctuations in the initial number. I think it's from 0 to maybe 15 or 20. And we don't see it affecting too much in terms of these sort of average quantities that we're observing here. So I think as long as the initial excitation number is small, right, so the order of 10, then when we're observing the system, you know, with 100 or more Rydberg excitations, it seems relatively robust. Any other questions here before I move on to the next experiment?
How does
Go ahead.
dimensionality play into this? You made a point of doing this in a 2-dimensional gas, but we see the same thing if it was 3D or 1D, or would just rates change, or would the overall behavior change?
We see, because we can also do 3D, and the next experiments are actually in fact done in a 3D volume, we see again qualitatively the same behavior in 3D. In 2D, it's a little bit cleaner for us because we can sort of control the finite size effects a little bit more. In principle, the universality, this directed percolation universality class, it depends on the dimensionality. So you would expect to see critical exponents which depend on the dimensionality of our system. And in fact, that's how we got into this game. We thought, okay, we'll measure in 2D, and then we could use some scaling relations and see a clear difference. But it seems that the scaling properties of this system are interesting, but not the same as you would expect for directed percolation. So I would say that the dimensional dependence is still interesting and open.
So I have another question. In real epidemics, unfortunately, there are also deaths. So basically, in this case, would be loss of atoms. So so can you do something like, for example, just switching on the channeltron and see how many Rydbergs you have, and then keep going with the simulation and inducing a loss a little bit to actually do this?
In fact, we already have a loss, and this loss is negligible for these short times, but is extremely important for the later time dynamics, which I'm going to show you. Okay.
What limits the location where the incidence rate just like flattens? So you have this growth, and then it starts flattening. So what limits that, or what sets that?
Yeah. So as far as we can tell, I think it's somehow limited by the system size, but maybe in a non-trivial way. So I'll come back to this as well. I'm promising a lot of things now, so I hope I have time. So it's somehow, it's a saturation of the system, but just to a density which is much lower than we would naively expect based on just simply comparing scales, the facilitation rate and the cloud size. Okay, I'll come back. Okay, so the second experiment I wanted to present concerns the late time dynamics. So in this first experiment, we looked at maybe 5 or 10 times the lifetime of the Rydberg excitations. And it was in a window where we could more or less neglect the fact that eventually some of the atoms are leaking from the trap. In fact, when Rydberg atoms decay in our experiment, there's a probability also that they decay entirely from the trap and are lost from the system, right? And so this plays an important role in the late time dynamics and actually gives rise to some new physics, which we were able to associate with the phenomenon of self-organized criticality. And I'll say a few more words about this in a moment. But our observation, which led us down this path, was basically this measurement here. So this is now looking at the total number of ground state atoms left in the trap. So not the Rydberg excitations anymore, but the remaining ground state atoms as a function of time. And you can see up to 10 milliseconds now, so much longer time scales. And what we see is that at early times, there's a bit of a plateau, then there's a rapid loss of particles, and then maybe something like a slow relaxation and an approach to a stationary density, which seems to be extremely robust. Even though the Rydberg excitation laser is on continuously, this stationary density seems to be preserved up to even 100 milliseconds. And for me, this was very unusual. This is a very nonlinear type of loss process, whereby you have a very fast loss initially, which is then cut off, and then the system reaches a final density, which is not zero, you know, and seems to live for a very long time. And what's more is if you do this experiment with different initial densities, so different numbers of particles in our trap, then we see qualitatively the same behavior, that, you know, there's a fast loss and then approach to a stationary state. But this stationary density seems to be rather insensitive to the initial density, right? So they all sort of asymptote to the same final density. That is, unless you start with a density which is below this final density, and then the dynamics is basically frozen at all times. You know? And it turns out that this stationary state that the system is evolving to is particularly interesting. And it's associated to this absorbing state phase transition that I showed you before. So these are basically initial conditions which are in a supercritical phase. The system evolves now in some way. Whereas here we start in a subcritical phase. So we never basically generate any activity, and the system dynamics basically stays frozen. And now we can understand this in terms of our simple cartoon picture before, you know, in addition to having a healthy atom and an infected atom, we can add a third process by which infected atoms are basically lost from the system. And this can be a number of different things. For example, Rydberg states they're not trapped in an optical trap, and in fact, they can even be expelled from the optical trap. They can also decay to other hyperfine ground states which are not resolved by our imaging system or the laser excitation. And so atoms, once they decay into this collective, let's say, zero state, basically they're lost from the system and no longer participate in the dynamics. So in the context of this epidemic model, we have our two processes, right? We can transmit the infection, we can recover, but now indeed we have a third process which can be interpreted as a death, or maybe if you're optimistic, then some kind of immunization process by which the dynamics basically stops. And this has an enormous effect on the dynamical features of this system, even in the limit where this loss is infinitesimally small. This is what I found most surprising, perhaps. And so you can understand this, for example, if you start in the active phase, right? Then basically you start with a large degree of activity, a lot of Rydberg excitations in the system, and they're gradually leaking out of the trap, right? And what this does then is depletes the remaining atomic gas now of population, so that the facilitation rate is getting smaller and smaller, right? And so that's a little bit like walking now your system along this line, right? So decreasing the facilitation probability until the system reaches the critical point, because at the critical point, basically the system enters this absorbing phase, you don't have many Rydberg excitations anymore, and so the loss basically stops. And so this is how we understand now the slow population loss as introducing an intrinsic feedback mechanism to the dynamics, which basically drives the system towards the critical point of this absorbing state phase transition. And this turns out to be one of the sort of paradigmatic ways to understand this phenomenon of self-organized criticality. So this is a fascinating concept. It was proposed 30 years ago by Bachtang and Wiesenfeld as an organizing principle that governs a class of dissipative coupled systems that can evolve naturally to a critical state while being insensitive to the parameters of the model. And that's what distinguishes self-organized criticality from ordinary phase transitions. You don't need any phase fine-tuning to reach the phase transition, right? But the system naturally evolves to the phase transition. And then there are, let's say, observable consequences of this associated, for example, to scaling laws and critical responses to perturbations. And what I like the most is it provides a very nice explanation for how systems become complex systems, and maybe even explains in some way why we see so many power laws or fractal-like structures in nature, whether this is, in the distribution of forest fires, in solar flares, in measurements of noise in neuronal activity or in electrical activity in complex circuits, and maybe even also in epidemics. But even though this has been studied now for more than 30 years, quite intensively, it turns out that this phenomenon of self-organized criticality is extremely hard to test under, let's say, controllable conditions. And we think this driven Rydberg gas provides one of the first, let's say, clear test beds for exploring this. So we came up with 3 signatures, more or less interpreting this phenomena in a way that can be observed in an experiment. So in order to let's say, convince ourselves that our system undergoes this self-organized criticality, we should have 3 main ingredients. The first one is that the system should self-organize to a stationary state which is independent of the initial conditions. This was the first graph that I showed you. Second, there should be some evidence of scaling variance in spatiotemporal correlations, as you would expect near a phase transition. And I'll show you an example of this concerning bulk observables. And you should have something to signify the critical nature of the system. So you should have somehow a very large amplified response to small perturbations. And I'll show you how this is manifest actually in our system in terms of these power law distributed avalanches, which is something like a smoking gun for self-organized criticality.
So Shannon, in your experiments, do you actually have to be at the critical point to see these sorts of phenomena? Because I thought you were seeing some remnants of this even when you were away from the critical point.
Yeah, this is a super interesting question, and it's still an open question, also an open theoretical question, because, and I'll mention this again, but theoretically, the conditions which are known to give you, let's say, a genuine self-organized criticality, precisely at the critical point, are very stringent. And it's hard to imagine in a real experiment how this would be achieved, right? And so there's been some generalizations of this idea, concepts called self-organized quasi-criticality, for example, where the system is sort of evolving close to the critical point, but not precisely at the critical point. And I think it's still an open question if this can explain the observations. And I think we have maybe it's a bit speculation still at this point, but maybe a nice way to understand now why we see signatures of criticality, even though maybe the system is not evolving, let's say, in a mathematical sense to the critical point. So this is the second experiment we did now. So it's very similar to the first. We just look at the final density of atoms in the system as a function of the driving field strength, right? So this is like the facilitation rate here. And again, we see this transition from an inactive phase where basically nothing happens to an active phase where we suddenly get loss. And so this final density is decreasing. And what you can see here is now for different densities, basically all of these curves show some kind of critical point, right? At which point the system enters into this active phase. And we argue self-organizes now to a final density, which only depends on this facilitation rate kappa. And to maybe prove this or show this more concretely, we can also do something you often do in studying equilibrium phase transitions. So we can use a scaling ansatz and rescale our data with some exponents here and achieve something called a data collapse, right? So where all of these previous curves basically fall onto one sort of characteristic curve, right, to a very good degree. And basically by looking at the scaling of this curve in an asymptotic regime, we can extract something like a critical exponent for the system. And so in this case, what we see is a power law exponent characterizing the system of 0.91, which differs significantly from what we would expect from a mean field argument. And so this is very reminiscent of what you know from equilibrium phase transitions. Here's the famous example for the liquid gas transition with different elements and molecular species, right, where you also get this data collapse, right? But the difference here, I should stress, is that here we don't do any fine tuning in order to reach the critical point. The system is naturally evolving towards this critical point. And so the emergence of this characteristic scaling is an intrinsic property of the system. And then the third experimental evidence is this critical response. So here now we look at the number of Rydberg atoms in the gas at different times. Keep in mind that each of these points corresponds to a new experimental measurement, right? At early times, we see this fast growth, which I discussed already, then plateaus. And then because of the particle loss, we see also that the Rydberg density starts to decrease, okay? But before it vanishes, basically we see a phase here of very large fluctuations. So what you see from shot to shot, basically, you see fluctuations from maybe 600 or 700 Rydberg excitations in the system to almost 0, right? And these are obviously not captured by the mean field ansatz, but we can do statistical analysis on these. So we sit, for example, I think this was 25 milliseconds out here somewhere, and we just measure 1,000 times what is the instantaneous number of Rydberg excitations in our gas. We make a histogram, and we see that the probability distribution nicely follows a power law distribution. Right? We can extract the exponent of this avalanche distribution. And this exponent actually agrees or is comparable to similar avalanching exponents seen in very different systems, ranging from forest fires to neural spiking and solar flares. And we don't yet have a good theoretical understanding of this precise number, but it's somehow reassuring that it somehow falls in the same range as other systems which are being conjectured, let's say, to be SOC-like. So some open questions. As I said, the conditions known to lead to SOC in theory are very stringent. So you need, for example, an infinite separation of timescales between, let's say, the fast bulk excitation dynamics and dissipation, which should strictly be only at the boundaries of the system. And this is not at all the case in our experiments, right? So this leads to the question, maybe, is this true criticality or only approximate criticality? And one problem with this is actually that in our experiment, we have a feedback mechanism by atom loss, which tunes the system towards the critical point from above. But we at least weren't aware of any competing process which would drive us back up to the critical point. And so that kind of rules out this notion of self-organized criticality, quasi-criticality, because if the system, let's say, undergoes an excursion into the absorbing phase, you would get stuck there. There's no mechanism to bring it back to the critical state. So it's kind of a bit mysterious why we see these characteristics of the critical state over such long timescales. Another question which is interesting maybe is what's the universality class? And can we correlate, let's say, this avalanche exponent to some underlying universality class like directed percolation? I think I should go a little bit fast here.
Can I ask a question anyway to slow you down further?
Sure.
So going back to your data collapse plot, so here these were just different densities, right? The different color data is different initial densities?
The different colors are different initial densities. Yeah.
So if you have other tuning parameters that if it's universal, it should also collapse with respect to, so kappa and all these other things. Have you tried that, and do you still get collapse?
Yeah, so this is the collapse with kappa, in fact, right? So we scale out the density, but it's equivalent to scaling out the facilitation rate, or you could do the rescaling in a slightly different way. So this is basically showing the scaling variance with respect to kappa. There is another parameter in the experiment, which is the detuning of the Rydberg excitation laser, which was fixed in the first experiments I showed. but we also confirm that for different detunings, and this has a very non-trivial effect actually, because it changes the facilitation radius and a few different things. It turns out this can also scale out. So you can get a data collapse in at least 2 of the experimental control parameters we know, plus the initial density. Yeah,
Yeah, very nice.
So there was one interesting observation that we didn't focus on initially, but turns out to be kind of crucial in our understanding, and that is that in addition to the peak atomic density, which we see self-organizing, we also have access to the spatial distribution, right? Which I said in the beginning we do through absorption imaging. And actually, when we do have a look at these absorption images, the raw absorption images, what we see is that the initial cloud has a Gaussian shape, which we expect from this pancake trap, right? After some few milliseconds of this self-organization, we see a dip forming in the center especially, right? And then on much longer times, it seems that this dip fills in, or at least the wings sort of flatten out, and we get an extremely robust flat top density profile. And so these are reconstructed from this using an inverse Abel transform. We can get the central density, and you see basically this sort of very nice flat top profile as the stationary state of the system, which turns out to be an additional signature of this self-organized criticality, right? And so to understand this, actually, we developed a better theory than what we had in the earlier work, based on an effective Langevin model, so with coarse graining and these things. But in this case now, including the fact that the particles can move in the trap. And in fact, we have a trap which is providing some restoring force, right? And so you get some hydrodynamic motion of the particles, which can redistribute and has some competition or interplay with the dynamics in the internal state degree of freedom. And it turns out, I don't show much here, but the experimental theory is in good agreement with each other. This is just one measure of the so-called excess kurtosis, which is measuring how flat this distribution is, showing that very good agreement. And in fact, even looking out to very long times now, you can watch the evolution of the system and watch how this flat top basically melts after some time, and the system reaches what we think is a thermal equilibrium state. And this showed us actually that there's a second mechanism that we overlooked initially, and that is, in addition to this particle loss, which brings us towards the critical state from below, we have a second self-organizing mechanism, which is basically this hydrodynamic flow of the atoms back in towards the center of the trap, right? That refills, let's say, the depletion due to these avalanching events, and sustains the critical state for very long times. And this is signified by this flat top profile, corresponding to the critical density for self-organized criticality. So we think that's a quite nice insight, and maybe explains why we can see these sort of critical features on long time scales, which wasn't initially apparent. The second aspect I wanted to highlight is that in analyzing the early time dynamics, we were inspired by these epidemic models to try and have a more quantitative understanding of the experimental data. And so we came up with a sort of a network type model, very similar to the ones used in studying epidemics, where we coarse grain the atomic gas into nodes. Here we use just a triangular lattice, right? And so we can say within a volume characteristic of the facilitation radius, we have a fixed number of particles, right? And so each cell of this coarse graining contains Ni particles, and each cell can be either susceptible, meaning there's no Rydberg excitations there, but you have a few ground state atoms. It can be infected, which means there's a single Rydberg excitation in this region, or in principle, and we don't need to use this for the early time dynamics, but you could also have cells which have been depleted of population and therefore removed from the system. And so now a crucial aspect of this model, which we found is needed to describe the experimental data, is that the infection probability between two cells should be weighted by the number of particles in the adjacent cell, right? And so what that means is we have some kind of disorder in our system, or heterogeneity of the network, because depending on our density and the size of these cells, we might even have regions of space where there is no atoms to facilitate, right? And so this has an enormous effect on the resulting network structure. And so we can write a sort of stochastic master equation for this thing, similar to the one I showed you before, but now including the connectivity of the network, right? And these weights governing the facilitation probability, which turns out to be very similar to the kinds of metapopulation models which are really used to study epidemics. And it turns out to be a remarkably efficient way to study the dynamics of our system. So this is a experimental theory comparison. The solid lines are the results of a Monte Carlo simulation, still fully classical here. And the main finding is that both this sub-exponential growth and the final stationary density is very strongly dependent on the degree of heterogeneity in this underlying network model, controlled by the mean number of excitations per mean number of atoms per cell. And this was puzzling to us because, in fact, inside the atomic gas, the atoms are moving with relatively high velocities. So we estimate the thermal velocity is around 60 micrometers per microsecond. So they move several facilitation radii within their lifetime. And so initially we were expecting this sort of role of disorder to be washed out and not very important. But it turns out that there is some kind of quasi-static or effectively static disorder, which we can understand if we include the fact that this facilitation condition is not only position dependent, but also depends on the velocity of the atoms. We have an argument based on Landau-Zener transition probabilities and so on, right? Which then implies that the system has some kind of static structure which evolves very slowly in phase space and can then explain the important role of heterogeneity in this system. And the second observation we find from this network model, which we would like to explore a little bit further, is that if we look here at this late time relaxation, it turns out in the experiment, and even more so in the theory, that there's a very slow power law relaxation here, which is a hallmark of a so-called Griffiths phase. So this is where you have very strong disorder effects or heterogeneity. And this gives rise to these sort of exponentially rare regions where you have maybe supercritical dynamics. And when you average over these rare regions, you expect to see characteristics of let's say, critical fluctuations, but with non-universal power laws. And so now we think we have maybe an understanding of what's going on near this absorbing state phase transition. So it's probably not just a transition from an absorbing state to an active state like you would expect for directed percolation, but rather these two phases are separated by something like a Griffiths phase, which is strongly affected by heterogeneity in this system. So there I think I should stop. So maybe just to quickly summarize, hopefully I've convinced you that this system is a very exciting sort of playground for studying complex system dynamics. We see it as something between, let's say, empirical observations where you have very little flexibility to control the system, and the kind of abstract mathematical models which are typically used to describe these complex systems. I show you two experiments on the early time growth dynamics, right, which has some kind of universal characteristics. And then also at late times where particle loss plays a role, we see this self-organizing behavior. And now I think an interesting question is if these Griffiths effects also persist on these very long time scales, and perhaps even this could explain now the emergence of power laws in these self-organizing systems, perhaps with non-universal exponents. And then finally, I showed you how you can use these sort of emergent network description to nicely link between microscopic and macroscopic regimes, which is extremely difficult in studying complex systems. So that's it. Maybe just one word on the future. We recently upgraded our experiment so we can also spatially structure the atomic ensembles. So we can create these sort of nice lattices or even quasi-crystalline systems or programmable disorder. So each one of these dots is a tiny atomic ensemble which would carry one Rydberg excitation. So it'd be extremely interesting to study this kind of network dynamics now on these kind of programmable systems. And we're also interested in pushing our system more into a quantum coherent dynamics regime. We have a recent paper in PRL, a theoretical paper analyzing the dynamics of this driven Rydberg gas, and we find a nice mapping to what's called quantum cellular automata, which is a sort of a nice model for exploring complex system dynamics, but also can be used, for example, in quantum computing. with that, that's all. This is my group, and yeah, we have a lot of good collaborators on this work. In particular, we have a lot of interactions with Sebastian Diel and Michel Buchhold in Cologne. So that's all. Thank you all for your attention.
So-
Shannon, that was very, very nice. We have any more questions? We had some good ones during the talk.
So I had a question going back. Well, actually, I had two questions. So one is basically all of the theory and sort of understanding you had of what you were seeing came from a more or less classical place, these classical master equations and stochastic growth models things. Does that mean this is a classical system, or do you think there are remnants of the quantum mechanics here that are important? And regardless, you had mentioned that you were thinking about ways to introduce the quantum mechanics into this. Can you just discuss how that would work and when it would become important?
Yeah, so everything I showed you today, I think can be understood very well within these classical models. And in fact, in the self-organized criticality paper, together with Sebastian and Michel, they derived more formally this sort of classical Langevin equation, starting from a quantum master equation, right, which we know describes the driven dissipative dynamics of these Rydberg systems quite well. But in the experiment, we have quite strong dephasing from various sources, the laser line width, the motion of the particles, and so on. Plus, it seems when you do the coarse graining and look on these very long time scales compared to the lifetime, that these quantum effects don't seem to matter too much. All right, so it doesn't mean that it wouldn't affect anything, but at least for our observables, it's not so important. So I think the key would be to cut down on this dephasing. And it's feasible to get line widths down to maybe 1 kilohertz, which is smaller than the lifetime of the Rydberg state. This is smaller than the facilitation rate. And then I would expect coherent dynamics for, let's say, a few branching events, or let's say excitation timescales. And that's more or less the regime we studied in this quantum cellular automata. Yeah. Doing this in experiment is still a bit challenging, but I think it's possible to do so. In particular, with these tweezer traps I showed at the end, and there's great work, for example, in Harvard and Palazzo and so on, showing coherent dynamics in these Rydberg ensembles. I think it's feasible to explore some of the analogous effects.
Thanks.
So when you were describing the end of your talk, where diffusion was playing an important role, I guess you're saying you're not in the frozen gas regime because it's taking too long. Is there any hope of driving the system harder and getting it into the regime where all this dynamics happens on a faster time scale, where you could be in that regime?
You would like to see what happens in the frozen regime, you mean?
Yeah, where the diffusion isn't so much a part of it. I guess that'd be hard. That time scale would have to be pretty fast.
I mean, we could certainly cool the atoms. I think it's easy to go a factor of 10 lower in temperature, even in our experiments. I think the issue is that we look on very long timescales, even compared to the Rydberg lifetime. And so probably in that case, the best way to see something like frozen dynamics is by pinning the atoms in space using these tweezers. And what we showed in our experiments is that we can do this on a relatively large scale. So we can create more than 400 of these tweezer traps, which would already be quite interesting. And then you could even explore like finite size effects by changing the number of tweezers and so on.
I do have a question. So can you go back a couple of slides to
try? Yes.
No, the next one, like the final one when you presented the entire process. That one.
This one?
Yeah.
Mm-hmm.
No, the previous one, but
Previous?
with the two graphs. The next one, next plot. So that one has another plot that at the end you have the relaxation process too, like the self-organizing process.
Ah, yes, in the, yeah.
That one, yeah. So on biological and metabolic networks, you do have similar like curves regarding like feed forward motives of networks or things like that. When you have like feedback, positive and negative, that you have like a response to an instantaneous stimulus. So I was wondering, because on those systems, you could also have like, if you can tune properly the positive and negative feedbacks, you could also have like an oscillation of concentration instead of just reaching a plateau. Have you like, I don't know, explored those types of tunings of the parameters in such that you can have like a oscillating, changing the number of excitations or things like that?
Yes, so I mean, you could do it obviously with some external control. You could modulate some of the control parameters, and you would get some oscillations. We do see in some of the numerics, not so much in the experiment, but in particular where we have this hydrodynamic feedback mechanism also. So here, where we have these two processes, it looks as though, and probably I should refer you to my collaborator, Michel, for details, but it looks as though depending on the ratio of this refilling rate and the loss rate, so these two competing feedback mechanisms, you can get something like oscillatory dynamics. And we're still trying to understand this. So if this is already understood in biological systems and maybe soft matter, that would be extremely interesting to find the analogy.
Yeah, I think that the easiest case is like predator-prey systems that are the most simplified ones that you can have oscillations, but there are also like regulatory networks for proteins or things like that you actually see like that, those cycles, and depend obviously on like ratios of the, I don't know, the degradation of the protein rate and other stuff. So
yeah, we should definitely look into this. I think it's an interesting topic.
Thank you.
Great. Well, maybe we should wrap up and let Shannon go and everybody else go as well. But thanks a lot, Shannon. Let's all thank him one more time for a really nice talk.